Record to cloud. Nice. Mm-hmm. 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 Yeah, so thank you all for coming for the second day. Last time we discussed a lot of stuff, but we didn't actually discuss what are the models, how they design, how they look like. And today we'll cover part of this, and the next part will be tomorrow. So let's recap a couple of things. First of all, training scheme. As you remember, we need to train our models, and training is an iterative process, which can be summarized in 3 simple steps. You get data, you calculate forward step, you do forward step to calculate loss, and you do backward step to update your model. And all we said about the model is that it is just some computational graph. We can look at this model as a computational graph, just a stack of layers that return new output given the output of previous layers. Yeah, if we have such example with 4 layers, layer 1 takes input data and produces some output. Layer 2 uses this output to produce its own output. Layer 3 uses layer 2, layer 4 uses layer 3 and layer 2. So it is possible to use outputs of several previous layers. Yeah, and layer 4 returns your final output. Yeah, so one layer is just some function that uses previous layer's outputs or input data to calculate new output. But what do I mean here by some function? Actually, it can be absolutely any function with one star here that ideally should be differentiable, or for which we can do some tricks at non-differentiable points. So PyTorch will figure it out for you, and if it can not, there are maybe some examples with if you do some custom layer yourself, maybe you will need to define how to do proper gradients yourself. But usually PyTorch will do everything for you, so you mostly do not care. Yeah, and the definition of what is a layer is not very strict. At least I haven't heard like a strict definition that everyone should say that layer is this and this. So I would define it like this. You can say that a layer is absolutely any function. And if you want, you can simplify it and make one layer look like 2 layers. For example, you have one layer which does 2 multiplied by sinus of its input. And you can say that this is one layer. But if you want, you can say that this is 2 layers. First one calculates the sinus, and the second one multiplies stuff by 2. We actually do not care, and PyTorch will do this kind of stuff inside. Instead of calculating this directly, it will calculate at first sinus and then multiply it by 2. So what is layer is mostly about how you want to visualize your model. So if you want to visualize it in 3 blocks with 1 layer, you can do like this. If you want to visualize it with 2 layers and 4 blocks, you can do it like this. So it's up to you. But yeah, so layer are just some simple or some more complicated functions. But in deep learning, there are many standard layers. So they're so commonly used that some functions have their own name, and this function like does a certain stuff. For example, there is fully connected layer, which we'll cover in the next slide. Convolutional layer, which we'll cover today. Boolean layer also will cover it today. And sometimes when you visualize your network in these blocks, you can even say that the whole neural network becomes like one layer, because such neural network becomes so usual, so popular, and used in so many designs that usually people just say, okay, you have one block, and that's the whole neural network. And a recurrent neural network, which we'll cover also today in the second part of the day, and transformer sometimes are just used as one whole block. Yeah, so questions? No? Good. So let's start with fully connected layer. This is probably the simplest type of layers. And it works as follows. You have your input, which is a vector. So here in this example, your vector has a size of 4. Yeah, 4 nodes. First one, second one, third one, fourth one. And one layer, FC layer number 1, converts this vector of size 4 to a vector of size 6. And you have 6 nodes here in this visualization. How it does this? As you see, each node is connected to each node from the previous layer. So this node is connected to the first input element, second input element, third input element, and fourth input element. And the result is the weighted sum of this node. So to get this node, you need to use this element multiplied by some weight, sum it with this element multiplied by some another weight, this element plus some another weight, and this element plus some another weight. For this node, you do the same stuff, but you have different weights. So it's again this node multiplied by some weight, this node multiplied by some another weight, this node multiplied by some another weight, and this node multiplied by some also another weight. Yeah, so fully connected, it's called fully connected because as you see, each node is connected to all previous ones. If you know like graphs in mathematics, yeah, fully connected graph is looks like this. Yeah, and here there might be misleading notation. As you see on the picture, there is so-called input layer, hidden layer, and output layer. But actually, there are only 2 layers here. First, fully connected layer that converts inputs to these nodes, and another fully connected layer that converts this vector to this vector. So the picture from the previous slide is equivalent to this one. You have your input, you have your hidden layer. Here you will get a vector of size 6. You have your output layer, which produces the final output vector. So in some literature, the last final layer in the scheme sometimes is called the output layer, and all other layers, so everything except the final layer, are called hidden layers. They're hidden because they're like not the final one. And also in the literature, you may see such thing as MLP, multi-layer perceptron, and this is just another name for a fully connected network. So if your network consists only of fully connected layers, it looks like this, or like this picture on the right, it's called a multi-layer perceptron. Sometimes there are different notations of how many layers you consider in MLP. So one may say that this is a 3-layer MLP and include input layer. So it says 1 input layer, 1 hidden layer, and 1 output layer. And this is 5-layer MLP, 1 input layer, 3 hidden layers, and 1 output layer. But in some another literature, people may say that you have only 2 layers because input layers doesn't count, or that you have 1 hidden layer and 3 hidden layers MLP, so they will count only hidden layers. Yeah.
One question: what is a perceptron? Is just a neuron?
Perceptron is like a strict name. I always consider that perceptron is just like neurons that are connected to each other. And one node is called one neuron. And when neurons are connected to each other like this, it is called perceptron. I'm hoping correct.
So the history of this type of network is from trying to understand how the brain works. We're not trying to do that here, but it's just because.
Yeah. So originally, and the whole name deep neural networks and neural networks is that because we want to understand how neural processes work.
We need not the brain to this.
Yeah, we say that our brain has neurons that are connected to each other somehow, and each node here is also called the neuron sometimes. And if neurons are connected to each other in a such format, it's called perceptron, or like also some brain stuff. Yeah, it doesn't really matter for us now. But yeah, thanks for the question. Yeah, let's give a more strict definition what is fully connected layer. So given input vector X, weights, matrix weights W, and bias vector B, we calculate such thing. So it's matrix vector multiplication WX plus B with sum with bias, and we pass this to so-called activation function sigma, also known as nonlinearity. So nonlinearity is just some function which is nonlinear, as you see from its name. And why do we need it? Imagine we won't have this sigma, and we only do WX plus B without any activation function. And imagine you have two layers, two fully connected layers, one after another. One with weights W1, B1, and another with W2, B2. Then if you calculate them one after another, you calculate such stuff. You can open the brackets and create a new ones. It will be like this. And let's define W2, W1 as W3, and W2, B1 plus B2 as B3. Yeah, and we got also something which looks like a fully connected layer. This means that if we don't have nonlinearity, there is no point to stack different layers, because we can just use one layer and achieve the same result. Because this operation is linear, this operation is linear. Applying fully connected layer without nonlinearity is linear. If you apply two fully connected layers in such way, because it's a linear function after linear function, you get linear function. So there won't be any sense to stack layers if you don't have nonlinearity. Also, with linear functions, we can't approximate nonlinear functions. And usually, when you want to do complicated stuff, you don't have linear functions. So this activation function allows you to makes sense to stack layers, and also allows you to approximate nonlinear functions. Nonlinearity can be, there are tons of variations of nonlinearity. And here are some examples. For example, there is sigmoid. It works element-wise and applies this function element-wise. One common is ReLU. It just takes the maximum of X and 0. So it cuts everything which is negative and makes it 0. Leaky ReLU is similar, but instead of saying that negative values are 0, it just it has some slope, so they're not 0 directly. YeLU is also something similar to ReLU. Max out have some weights and chooses max here, so it's not a popular activation. Yeah.
When we work with very huge amounts of data, then ReLU and tangent and sigmoid, all of this doesn't really make sense. Like, is there a moment where choosing a function is better than another, or?
Yes. So the question for Zoom people is when to choose which function. So each function has its own properties for conversions, for everything. Like there is a theory behind it. For example, there is a famous CLU paper which contains only 10 papers, but its appendix has like 200 papers, 200 pages. Sorry. Yeah. So people investigate these activation functions and say, like, what are the properties when one function works better than another. Sigmoid was a very popular function at the start of deep neural network studies, when all the studies began. And as we will see, I guess, today in RNN lecture, sigmoid might not be the best choice, because if you have too many layers, after some time, gradients from sigmoid will make the norm of your gradients as smaller. And it might be the case that if you use only sigmoid activations, your first layer won't get any gradients. The gradient norm will be close to 0 because sigmoid doesn't have the best what's called differential. ReLU, people usually use ReLU, but there is some theory behind leaky ReLU or similar to it like CLU or GELU that doing this negative making all negative elements equal to 0 is not the best choice. So people usually use the leaky ReLU now or CLU, GELU, which are kind of similar but have some other properties behind them. Sigmoid and Tanch might be a good choice for generative adversarial networks, for generating images, because when you generate images, your final output should be between 0 and 1. Because the image in computer is usually is in uint unsigned integer 8, so it's some number from 0 to 255. If you move it to floating points, it will be from 0 to 1. And your network should output something which is between 0 and 1. And what people usually do, they say, okay, my final layer will have activation with a sigmoid, and the sigmoid will return something which is between 1 and 0, and that's what we want to. And also in classification, sigmoid, it's applied internally in loss functions. So you don't use sigmoid in your network, but when you calculate loss, the sigmoid will be applied to get probabilities. Tanch is also used in GANs, but for similar reason, but you want to have your images in -1, 1. Because there is some theory that having images between 0 and 1 is not stable. So you at first achieve image from -1 to 1, and then you normalize it back to 0, 1 by dividing it by 2 and having bias 0.5, something like this, okay? More questions? No. Okay, let's have one example. I edit it at night because you suggest me to get more examples. So you imagine you have a FC layer which converts input from R2 to R3. And here are your weights, here is your bias, and here is your input. Yes, you calculate WX, matrix vector multiplication. Then you sum the result with bias, like this. And imagine your activation function is ReLU. So ReLU of this will be 3, 11, 0, because 3 is greater than 0, so we keep it. 11 is greater than 0, so we keep it. -3 is negative, so we have a 0 instead of -3. Okay? Yeah, so in PyTorch, to define fully connected layer, you will need to choose input size, so dimension of the input, 2 in the example above. Output size, dimension of the output, 3 in the example above. And you also need to choose nonlinearity, like sigmoid, ReLU. But in PyTorch, nonlinearity is a separate entity. So in PyTorch, your fully connected layer is actually indeed linear. It's just WX plus B. And you apply nonlinearity afterwards, like you say, okay, you have a linear, and directly after this, in your computational graph, you will add nonlinearity yourself.
You have a line, let's say like the output, which is linear, and then you're giving it another function to make it non-linear. I didn't forget it.
Yeah, so we have fully connected layer should be defined like this. So you have, I don't know if people can see it on Zoom. No, I hope so. Yeah. Usually it's defined like this because you want to have nonlinearity to produce something nonlinear. But in PyTorch, what you usually do, you have like layer 1 equal, it will be called nn.linear, so it will be just wx plus b. And you will say like layer 1 activation and then dot reloop, for example. And when you will calculate the output, what you will do, you will say, okay, your output is layer 1 applied to your input x, and then you will say that your output is layer 1 activation applied to this result, like this. Okay? So people will see it in Zoom. I hope so. Yeah, so it should be defined like this. But in PyTorch, you will do it like this. And the reason for this is that there are tons of different activations, and it's reasonable to apply them like when you want to have a separate entity for this. And also, there might be the case when you don't want to have nonlinearity if you have like this layer is your final layer. So maybe you have like some nodes. You result with 2 nodes here. And maybe you don't want to apply a redo here. You allow for your final layer to have like negative numbers, maybe for some reason. So people usually don't apply activation for the final layer. And then this idea that we have separate entity for this stuff is reasonable. Okay. Questions? No? Fine. Good. Yeah, so fully connected layer has some problems. And the problem is connected with what if we have multi-dimensional input. So instead of having a vector, what if you have like an image, which is a matrix? How to apply fully connected layer with a matrix? One way is to flatten or reshape the whole input to a vector. So as you remember from previous seminar, and we'll have the image on the next slide, you have a matrix and you can reshape this tensor to look like a vector. So you flatten it. And then you have a vector and you can apply your fully connected layer as we discussed. But there are some problems. The first one is memory and computational costs. Imagine you have an image in a high resolution, 1024 by 1024 pixels. If you reshape it, flatten, you will get a vector of size more than 1 million. Yeah, so this is 2 to the power of 20, I guess, yeah? So in your fully connected layer, we'll need more than 1 million parameters just in the first layer to work with such vector. And this is bad. It's not efficient at all. Moreover, flattened data loses spatial information. So when you transform your image to a vector, and because fully connected layer considers each node independently, because all nodes are connected to because your layer is fully connected, there is like an edge to each node, and the fully connected layer won't know that some of the elements were neighbors in the original image. Let's look here. So you have multidimensional input like this on the left, and you flatten it like this. Yeah, so you have your first row, then you add the second row here, and the final row here. Yeah, and you receive a vector. Now your fully connected layer will look at all nodes. It will add edges to all nodes, and it won't know that, for example, green and red were close to each other in the original input. So you lose this spatial information, And this special information might be useful for you. Okay? Yeah, so to solve both problems, to save weights, memory, and computations, and also to preserve some spatial relations, we use convolutional layer instead. So instead of connecting each node with all others, we apply local filter with trainable weights, which are the same across the full input. If you had signal processing course, you should know what is convolution, but if not, so your weights are this filter, like small square here. Here you have some weights, and you put this mask, this filter over your image and go across it. Like this blue square, it is going across the image to produce output. Each time when you apply this filter on your image, you do weighted sum to calculate the output. Let's maybe draw it. Be easier to understand. You can also look at the GIF and see that how it calculates. But let's do like simple example. Yeah, so you have here 7, 4, 3, 2, 5, 3, and 3, 3, 2. This is like a part of your image. And your filter is like this, yeah, 1, 1, 1, 0, 0, 0, -1, -1, -1. So what you do? You say, okay, we have 7, we use it with coefficient 1. We have 4, we use it with coefficient 1. We have 3, we use it with coefficient 1. We have 2 with coefficient 0. We have 3 with coefficient -1, and so on. So if we sum this, 7 plus 4 plus 3 plus 0 by 2 plus 0 by 5 plus 0 by 3 minus 3 minus 3 minus 2, we will get 6. And as you see on the slide, here we got 6. And if we move this filter from this position to this position, we will again calculate weighted sum, and we will get -9 as GIF suggests. Okay? Questions?
Filters, like when you're choosing 1, 0, -1, or if it's like rule sum.
So here is just an example for with 1, 0, -1. Usually you will use trainable filters. So this your neural network will learn these weights. So with this gradient stuff, backward step, instead of having like 1, 0, -1, you will have W1, W2, W3, and so on. And with gradients, you will update W1 with some new value, W2 with some new value, and so on. But this filter here, I guess in signal processing, there is some name behind it, starting with S, I don't remember. So this kind of filter usually is applied to calculate edges on the image. So if you want to detect where the edges, you apply such kind of filter. Yeah, and one note here, that the output of a convolutional layer is usually called feature map. So if you find in the literature something which is called feature map, usually this is the output of a convolutional layer. Yeah, convolutional layer can be applied to multi-channel image. So you have, yeah. Sorry. Fine. Yeah, so if you have several channels, for example, RGB image, there is one filter per each channel. So you have one filter for first channel, for red channel, one filter for green channel, one filter for blue channel. You apply the GIF from the previous slide on each channel independently. calculate one number here, one number here, one number here, you sum it, and you may have again bias, and you sum these three numbers with this bias, and you get one number. So from 3 channels, you have only one output channel here. So you use all 3 channels to calculate one output channel. Okay? I see you have.
For me, can you repeat or explain more the concept of the channels? Because in this case, it's RGB image, but I'm not sure you can use other example.
Yes, so the concept of a channel is as follows.
Or other kind of my question, how do you know how many channels have your image?
Yeah, so usually if you like apply convolution to your input data, so your input data here, like some image, yeah, it will have usually 3 channels if it's RGB, 1 channel if it's grayscale, so only black and white, and it may have like 4 channels if it's not RGB, it's not grayscale, it's some fancy SMY. CMYK, SMYK. Yeah, so if you have something like this, you will have 4 channels.
But I mean, it only depends on the color of the picture.
So if your convolution layer is your first layer in your network, it only depends on the input you use, like on the image, how your image is defined. If you want, you can transform your RGB image to grayscale one. Like you, instead of using 3 channels, a colored image, you'll have only gray, black and white image. Yeah, but in your network, as we'll see in the next slide, you can resolve in how many channels you want. So you can convert 3 channels to something with, I don't know, like 32 channels, then with something with 64 channels, then with something with, again, 32 channels, and maybe you want to have 1 output channel. Yeah, so your network can transform 3 channels image from 3 to 32, then from 32 to 64, then from 64 to 33, and then from 32 to 1. I missed the numbers when I said them, but I hope you understand. Yeah, so, and here your convolution will be applied to input with 3 channels and produce 32 output channels. Here your new convolutional layer will be applied to input with 32 channels and be used to produce 64 channels and so on. So if you have here, instead of 3 RGB image, you have like maybe your intermediate output, which has 32 channels, you will have 32 filters here, okay? And all these filters will be applied to their own channel. The result will be summed, and your output will have only 1 channel. If you want to have questions, no? If you want to have multiple output channels, you just add more filters. So here, the colors might be misleading, so it's not RGB. I mean, this red, blue, and green. So imagine you want to have 4 output channels. Then, for example, for this blue output channel, you will have 3 blue filters here, 1, 2, 3, and each of these blue filters, sorry, will be applied to one of the 3 input channels in the image. Okay. Let's see maybe this visualization. Maybe it's easier. So your input has 3 channels, and you want your output to have 4 channels. Then you will have 4 different filters, and each filter inside will also have 3 parts. Like one big filter consists of 3 small filters. one for this channel, one for this channel, and one for this channel. And this large filter will result in only one channel. If you want to have second channel, you will use this filter. If you want to have third channel, you will use this filter, and so on. And all these filters have their own different weights, which are trainable by your deep neural network. Questions? Or I see some eyes that you're maybe.
Yeah, so how does the bias work? You showed the, is that, so you've got a filter that's got 9, in this example, you've got 9 times 3 weights, and then there's a single bias for every pixel, or a single bias for the whole?
I guess here.
I've not thought about biases.
Let me recall.
So for every
No, it's not a single scalar.
not super important, don't worry about it.
Yeah, we can look at this in the code. We can access these weights and see their shape, and then instead from this, I don't remember right now. Sorry. Parsa, maybe you remember. Bias in convolutional layers, is it still a vector or? Can you check in PyTorch, like create a layer conv2d and see how bias look like? Yeah, while Parsa is searching, let's go further. So to define convolutional layer, again, you will have to identify how many input channels you have. If you have RGB image, it will be 3 channels, but if like it's your intermediate layer, like I showed here, maybe your input channels will be like 32. Okay. Output channels also, how many output channels you want. 4 in the example above. Also, there are much more hyperparameters, like much more things to choose, and we will discuss them in the next slide. But again, don't forget about nonlinearity, and that this is in PyTorch as a separate entity. So in PyTorch, you will apply convolution, and then you will apply a second layer with an n.relu or sigmoid or anything else.
So yeah, the bias is a vector, but you should broadcast it when you want to add. So
yeah, but its shape is defined by the number of filters.
Like n1.
And n is the output, is the number of output channels.
Yeah. Exactly.
Okay, so the bias is the same for one output channel. So here will be the same bias for each element of the result. But if you have multiple output channels, each of these channels will have its own bias.
Channels are independent, actually.
Yeah, output channels are independent. Yeah, thank you, Parsa. Yeah, so if we look carefully at the convolution, you will notice that that's also a linear operation. Like you can write it as a very complicated matrix matrix multiplication. So for the same reasons, you also need to use nonlinearity. And yeah, so never forget about nonlinearity. There are more parameters here in the convolutional layer. One of them is called kernel size, also known as the size of the filter. So here in dark blue, you have your filter size. Here it is 3 by 3. But it is also possible that you have a filter of size 4 by 4, or even 3 by 2. I just didn't find a GIF for this. But yeah, your filter size can be any as you want. And it will say how it will define how you calculate this weighted sum to get the result. Don't look at this white stuff here. We will cover it in the next slide, I guess. Okay, so kernel size. Yes, hyperparameter to choose when you define convolutional layer. Good? Good. Yeah, so another thing is stride. So stride is the hop size between application of the filter. So here on the left, you have stride 1, So as you see, your filter moves one element to the right and one element down. But it is possible that you have a stride too, like here, and you see that your filter moves by two elements all the time. Also, stride can be different for y and x axis, so you can move by one element to the right and by two elements when you go down, for example. Okay. I guess a GIF is pretty good, so should be okay. Yeah.
Why would you do that?
Why would you do stride?
Yeah.
To save memory and computational costs. So because moving by one is expensive. Like if you have a very large image, a very large input, you will go, and you will need to do a lot of calculations. But if you have stride 2, you can skip part of the calculations. You still will use the whole image, but you will save computations.
That's the comment. So that's why when we are, let's say if we are applying this convolution layer for an image, the quality will get more blurred, right? Is it because of it? Can we say it? If you apply to image, high quality image like this kind of convolution layer, it will get blurred.
With a stride, you mean? No, I would say that this depends on the filter weights. Yeah. So the question for the people was, is stride the reason why images can become blurry after application of the filter? I would say no, because if you choose weights properly, there is like a Gaussian image filter, as far as I remember. And if you choose weights properly, you will already get a blurred image, but with stride 1. Oh, yeah. Yeah, also there is padding. So padding is, yeah, maybe I forgot to say this. Yeah, also, as you see, if you choose different stride, your output will have a different size. So here with stride 1, you had 3x3 output, and here you have 2x2. And maybe if you want to reduce the size of your image, you can use stride 2. For example, if you have 4x4 filter, and you use it with a stride 2 and 2, you will be able to reduce the size of each dimension by 2. So if you had like a 44x44 image, using such filter and such stride, you will get 32x32 output result. And that's like the common way to do it. You can do the same thing, but using like 3x3 stride 1 and padding, I guess. Like there might be different ways to achieve the same stuff, but like 4x4 and stride 2x2 is a common one. Yeah, I said padding. So padding just pads your input to make your output feature map larger if you need so. So we have the same blue input here and the same green filter 3x3. But we also did padding of size 1, so each dimension now has one extra element in gray. And now you see that you can cover the borders more often. So instead of applying one filter just here, just here, you can apply a filter here, here, and so on. So first thing padding allows you to do is to get a larger output feature map. And the second thing it allows you to do is it allows you to look at the corners or borders more often, because without padding, this information is not used often. And maybe you want to use it, like if there is some important information in these corners, in these borders, maybe you want to do padding to use these elements more often. This padding can be done with zeros. It can be done with some interpolation or maybe with reflection. So maybe you like use your image and you like make a symmetric one to pad. So there are different schemes. Usually you use padding by 0. Yeah, another concept here is called receptive field. So receptive field is the part of the original input the current element depends on. So if you look here at this red square, if you have filter 3 by 3, your input here, your result here depends on these elements from the original input. And this one on layer 3 depends on these 3 elements, 3 by 3 square, sorry. And if you look carefully, you will notice that actually the result from layer 3 depends on the whole input image. So receptive field for this element is the whole input. And there is such concept as dilation. So dilation is the inner spacing in filter. Instead of having 3 by 3 filter like this, and having with dilation 2, you can make your filter look a bit weird like this. So it looks like 5 by 5, but you skip okay, how can I stop it? I guess you see it here, yeah. So instead of applying to a square, we apply to a strange kind of square where we skip some elements. And this is used to increase receptive field, as we can see from this example. Here we have our input. Here we use dilation 1, so everything is usual. We use each input. Here we use dilation 2, so we skip one element. Here we use dilation 4, so we skip 3 elements. Here we use dilation 8, so we skip 7 elements. And if you look at this output carefully, you will notice that it depends on the whole input. And the receptive field for this output is the whole input. And we did it only by having 1, 2, 3, 4 convolutions. So we saved some computations and increased receptive field. And maybe in your case, receptive field is very important because maybe you want your result to depend on the whole input or to the very large part of your input, not only on some local features. Yeah, here in this image, we have first we have one-dimensional convolution, so it's not mandatory to have a 2D filter. Like in signal processing, you have one-dimensional filters. The concept is exactly the same, but instead of having x-axis and y-axis, you have only an x-axis. Okay. And here also they are causal. In signal processing, you also have this kind of definition. So you don't look into the future. So if you have one-dimensional convolutions and you have a sequence, like x1, x2, x3. So, and you want a result here for x2. So your non-causal convolution may use this input, and your causal convolution won't look at x3 because we are at the timestamp number 2. Yeah, so 3 is a future. Maybe we don't want to look at it, so we will use like only a part of the filter and apply only the filter to x1 and x2. It is called causal convolution. And it's not like popular, I would say. It depends severely on which task you want to do. Yeah, and also, yeah, from convolutional layer, that's all. That's all the parameters you may want to consider. And now we have pooling layer. So pooling layer applies some function instead of convolution, but also filter-wise. So instead of having this weighted sum as your filter, you might have a different operation, and you don't have learnable parameters. So you also save some memory here. For example, your pooling layer may do max pooling. Here you have filter of size 2 by 2, and you will choose the maximum element. So here you have 1, 3, 0, 8. Your maximum element is 8. Here 2, 5, 7, 0. Your maximum element is 7, and so on. And you can have, for example, average pooling. Average pooling will do something like convolution, but with fixed weights, 1, 1, 1, 1, 1, 1, 1. So you just have not 1, 1, 1, because it will be 1 over n. So you can have max pooling, have average pooling. There are some other pooling layers, but the idea is that you apply some function instead of training weights. Okay. So convolutional neural network, the general structure will look something like this. You have your input, you apply convolution plus some nonlinearity. Then maybe you want to do pooling, maybe you want to do like another convolution plus nonlinearity, maybe some another pooling. And then you can use MLP head above it. Like you make your image smaller, and after some point, maybe flattening is not so bad. Maybe you don't care about spatial information anymore because you already compressed your image in such ways like that the inner representation is good enough. There's some question in the chat. In which situation could we want to use pooling layer? Sorry for this slide. No, let me finish this slide and then I will come back to the question, okay? So general structure may look like this. And after some number of convolutions, poolings, all this stuff, maybe you already compressed your image, got some representation, which already contains all information you need. And all what is left to do is to apply some classification head to do, for example, classification task. And then you can flatten your image to one-dimensional vector, and do these fully connected layers that we discussed before. Pooling layer. So question was, when do we need pooling layers instead of convolution layers? So as I said, pooling, and I also forgot to say that pooling layers also have the kernel size, stride, padding, dilation, and all this stuff that convolution layers have. So first time that you want to use pooling layer is when you want to save memory and you want to reduce the dimensions. For example, you had 520 by 520 image. You apply some convolutions, but your result may be still 520 by 520. And instead of doing another convolution that will learn how to reduce image to 256 by 256, you just apply max pooling that will do this operation without any trainable weights almost for free. I guess on the first day of the next week, when Federico will talk about computer vision, you will cover UNet. And in this UNet network, usually the pipeline looks like this. You have some convolutions, then you have pooling layer to reduce the dimension. Then you have another convolutions, and you have apply again pooling layer to reduce the dimensions and so on. The dimension size, sorry. Another example, maybe with average pooling, maybe you calculated some stuff here, and instead of doing some flattening, maybe you want to do average pooling, but to make it one-dimensional vector from image. Let me show it. So maybe you have like image like this, 2 by 2. Instead of getting a vector with 4 elements, maybe you think it is better to do average across this axis and get vector of size 2. So this element will contain average of this element, this vector. This element will contain average of this. Okay, so this might be the case. Maybe you want to do something like this. Then you apply average pooling. There is also such thing like adaptive average pooling, when you have images of different size, but you want to get a vector of fixed size. But we won't go into this today. It will be too much. Okay, so we are close to the end. One thing left to discuss is the residual connections. So let's recall backpropagation. As you see graph in GIFs here, you have your input layer, you do some forward pass, yeah, you make predictions, you get some output, you apply some loss function, calculate it, and you update your weights step by step using the gradients from this loss. Okay? Yep.
I heard someone saying that the forward pass is not the most important, and it's the back propagation that does all the more important work in prediction, and I wanted to know why.
So forward pass calculates the output, and if your model is already trained, you will never do backward pass. All you will do is forward pass, because given some input x, you want to calculate what is the DNN of x. Backward pass is mandatory if you want to train your model to update its weights to get a better approximation. So in this sense, yeah, backpropagation, backward pass does all the work to update the weights. But in order to use backward pass, you at first need to do forward pass to actually calculate the loss. You can't calculate the loss without forward pass.
But like the forward pass, can it be completely random? The calculation of each hidden layer.
No. Each layer is predefined by its weights and bias. They are fixed, and then they are updated when you do backward pass. Okay, so in your
You don't know what you should do. You don't know what the weights are, so they are. Then you apply learning. Maybe they're not. Maybe they're not.
yeah. Let's look at the fully connected layer, for example. Yeah, so you have wx plus b, and when you just start your deep neural network, your w, as your colleague here said, is a random matrix. So your output is random. It's definitely a better approximation. So so what you do at first, you calculate this result. Like you have some input from your data set, and you calculate FC of x. That's forward pass. Then you want to understand if you have a good approximation or not. Like you have your desired output also from the data set, and you calculate how similar is your FC of x to this y. You calculate this loss, the measure of similarity, and your backward pass will use gradients to update w and b. So w now is w minus some learning rate by some gradient. B is now b minus some learning rate by some another gradient. Yeah, so you will get new weights. They are not random anymore. They are random, but with like shifted by these gradients, and the approximation will become better. And you do this thousands of times, and after some time you will achieve FC of x, which is very close to y, and that's what you want to do. Okay. Yeah, so what if you have too many layers? Yeah, there might be a problem that you have so-called vanishing gradients. So the norm of the gradients make it around 0 for the first layers. So for the output, you calculate your loss, you calculate gradients, and maybe the norm of the gradients is huge. But it might be the case that the previous layer gets the gradient which whose norm is much smaller. Layer 2 gets a gradient with a norm even smaller, and so on. And maybe your first layer will get gradient which is close to 0, so it won't update the weights. Your weights will still be random, and that's bad. I guess Parser maybe will cover this. Will we cover vanishing gradients in RNN? Yeah, so Parser will cover it today in the second part. There is also such thing as exploding gradient. When your gradients increases, it might also happen in RNNs, I guess. Maybe we'll cover this too.
I'll refer to it.
Yeah, okay. Yeah, so just know that there might be some problems, but we won't go into too deep mess about it, at least right now. And another problem is stacking too many layers can lead to quality degradation. So empirically, it was shown that if you have your input data, some small model, and produce some output, and if you add more layers here, you may result in worse quality. And that's theoretically, that's strange. Why? Because imagine you have the same small model, and then you stack many identity layers. So identity layer doesn't change the output. It like f of x is equal to x. So you added many layers, and the output still is still the same because this is identity. But the number of layers increased. So if you have a larger model with the same small model at the beginning, in theory, it should learn this identity function. It should be able to learn this identity function. So at least the quality of a deeper model should be as high as the quality of a small model. You see? So in other words, where I put the chalk?
Yeah.
Yeah, so okay. Like imagine this is the space of all possible solutions with your small model. Your large model contains this small space inside. Why? Because it is also always possible to learn identity function. So this larger model should always get, after training, at least the same quality as a small model. But in practice, it might be the case when large model achieves worse quality. So this says that it's hard for deep neural network to learn this identity mapping. And to make it simpler for the model to learn this identity mapping, we add so-called residual connections, which actually I presented the previous day, but didn't say that this is called residual connections. So look here, imagine your small model is layer 1, layer 2, yeah? Now, because of this connection here, if you just say that layer 3 weights are 0, and layer 4 weights are 0, and you use only like this residual connection, you can still achieve the same output. So your layer 4, maybe it looks like this. It's layer 3 output plus layer 2 output. That's how your layer 4 works. You can say that layer 3 output is 0, and just use this error to achieve output. So it's easier for the model with residual connections to learn identity mapping, and this makes it easier to avoid this degradation problem. Yeah, Jeffrey.
So how do you know if your smaller model is better than the large model in the first place?
You train a small model, you train a large model without these residual connections, and you will notice that performance of the large model is much worse than performance of the small model. We'll see a plot in the next slide. Yeah, and also it helps with gradient flow, so it helps with this vanishing gradients problem, because now your gradients won't go just by these errors. They can go backward using this layer, using this error. arrow. So gradient from this goes here and here. Here it accumulates, and your layer 2 still can get an update even if these errors have small gradient, because you still have another gradient from this. Yeah, so this residual connection saves you both problems. Yeah, they were introduced in a paper which I don't remember how it's called, like residual connections, and they introduced the model named ResNet. So this is probably the most important architecture apart from transformers that you should learn during this week. Because if you want to solve any task, usually your model architecture will be based on ResNet. It will use ResNet or residual connections somewhere inside. Even transformer itself uses these residual connections. So that's was a very important point in deep learning history, because when ResNet appeared, everything became much simpler, and the models could become more deeper, more larger with ease just by using these residual connections. So we need to thank ResNet for LLMs and all this stuff, and for transformers. Yeah, so the main part of ResNet is this residual block. It looks like this. You have your input X, you apply some weight layer. In ResNet, it is convolutional, plus ReLU, plus another convolution, and you sum the result with identity mapping here, f at x plus x. Yeah, and notice that if you say that f at x is equal to 0, we have identity mapping for free. Yeah, so it's easier for us to learn this identity mapping. We can say that f at x is equal to 0. And making something equal to 0 is much simpler than getting identity function, because just set the weights to 0 and that's all. Sometimes here it can be something instead of identity. We'll cover this in the code. I hope you will have enough time for it. But yeah, original ResNet does identity function. Another useful part of ResNet is bottleneck on the right here. So it is used to also improve speed and reduce memory consumption. Imagine you have 256 channels in your image. And if you apply convolution directly with 256 input channels, it will be expensive. So what they suggest, you apply much, you reduce the dimensions, the number of channels using 1-by-1 convolution here. Then you apply the actual filter size, which you wanted to do like 3-by-3 in this reduced dimension. And then you apply another 1-by-1 convolution to increase the channels back to the number of channels that you wanted to do at the first place. Yeah.
How 1-by-1 convolution produces.
So as you remember, in convolution, one filter produces only one output channel. So let's go here. Yeah, so the number of filters inside this cube here is defined by the number of channels inside in your original input. Yeah, here it's 3, here it's 3. To calculate the number, to get different number of output channels, you need to have different number of these cubes. So 1-by-1 convolution has 256 channels inside, filters inside this cube, but instead of having 256 output channels, we will have only one for one cube, and we will use 64 cubes. Yeah, so sorry, I will show it here. So the idea is that your input was of certain size n by n, but with C channels. if you want to work with C channels with a 3x3, for example, filter, it will be expensive. So what they suggest using 1x1 convolution, so you don't change the actual dimensions here, so it will be still n by n. But instead of having C channels, you have like a C small number of channels. Now you can apply your 3x3 convolution to this reduced image. So that it reduces not n and n, but the number of channels. And it allows you to have not here in one cube, instead of having 256 filters, you will have only 64. And that's how it saves you computations, okay?
Thank you.
Yeah, so ResNet allows you to get very deep networks. I even couldn't feel it here. So here is a ResNet 34, and there exists ResNet 1001 or something like this. Yeah, so it wouldn't fit here. And you see there is the same network, but one with residual connections and one without them. Yeah, here, so one with residual connections and one does the same stuff, but without residuals. This is called like plain network, and this is a residual network. And if you compare the training scheme, you will see training curves. Sorry, you will see that plain network, so without residual connections, actually has this degradation problem. So the red curve is above the blue one, but this is a larger model. So even though that 30-layer network space, its space of solutions contains the space of solutions for plane 18, the result in practice can get worse. But if you apply these residual connections, the result for 34 layers gets even better than 18 layers, and that's what we wanted to have. Okay, we wanted to have at least the same quality, but actually we achieved even better quality. Here, error is not like another name for loss. It's 100 minus accuracy. It's another notation. Yeah, so it's like a accuracy plot. Yeah, and ResBlock can have different variations. So one apply activation after addition, one apply activation, one just do. So in the original ResNet, you do f at x plus x and then apply ReLU. But in your ResNets, what people actually do, they apply ReLU inside f at x and just say f at ReLU. They do ReLU f at x plus x. So they don't apply ReLU to the x itself. And it also helps with improving the quality. Here ResNet 1001, so it's like enormously large network, enormously deep, and it improves the performance. From the lecture, that's all. Do you have any questions, so we can move to the code? Yeah. Why using several previous layers makes it easier to train the model? Identity. Yeah, that's because your model here, what it does f at x plus x here, yeah? It's easier for model to learn that f at x is equal to 0 than to say that f at x is equal to x. Because to do f at x is equal to 0, all you need to do is to make your weights as small as possible. So make them close to 0. But to do identity, you can't say, well, what you need to do identity. Okay. It's another complicated task. Good. Yeah, let's move to the code. We have 25 minutes. I hope we'll be able to cover everything. Yeah, so from previous day, we import some stuff. And let's discuss how to create models in PyTorch. So in PyTorch, all models are instances of the class torch.nn.model. And to create your model, all you need to do is to define network layers and to define this forward step, which we discussed. So how to use these layers to calculate the output. You might know such method __call__. In classes, forward is just a wrapper around this, like alternative name for this call method. Just use forward and forget about the call. Yeah, backward step is defined automatically by PyTorch. So that's simple. You don't have to define backward yourself, unless you do some weird stuff with your own layers that you defined yourself, and maybe you want to do some strange version of backward step, then you still can write this backward yourself if you need to. But unless you know why you need a custom backward step, just trust PyTorch. The most popular layers are predefined in torch.nn.model. We can see documentation here. There are many layers, as you see, like transformer layers, recurrent layers, convolutional layers, Boolean layers. Many of them. And we can use whatever we want, or we can use custom layers, which we write ourselves. So let's import NN from Torch, and let's define model class. I named it my model. I say that it is an instance of an n.model. I guess in English it's better to say not instance, but like the child of the class. Let's say it like this. Yeah. Yeah. So like a subclass. Yeah. Instance of the object. So like subclass of the main class. Yeah. Will we come to the second day? No. That's the second part.
No, so I just have a train now.
Okay.
I will follow.
Yeah. So you define __ init and define some parameters that you want to choose. That you want some variables, some arguments, which might be useful to create like different models, maybe with different output size or with different input size. So you define them here. Before you initialize any layer, you need to call super brackets dot init brackets. So this runs the same init function, but for the parent class, for an n.model. So just do this before you initialize any layers. Then everything is pretty simple. You create a class variable using self.variable name. And for example, you can create fully connected layer, which in PyTorch is called the linear layer. You define input size, you define hidden size. Hidden size, like here, there's a. If you look at the signature, you have in features and input features and output features. And here I say that my input features are input size and my output features are equal to hidden size. Okay. Then I say I have activation nn.relu. I have another hidden layer. I have my final nn.linear. That's all. Now I want to define how to do forward step, how to calculate the actual output. Given some input data, I apply the variables sequentially. Yeah, apply self.net1 from input data, self.net2 of x, and x is here is the output of net1. Now net3 uses x from net2, and so on. And now from net5 I get my final output. Okay. Yeah, and we can create the instance of our class, my model, with, for example, we want to have input dimension of size 10, output dimension of size 2, output of size 2, and maybe our hidden features, we want to do them like 128. And we can print our model. It will look like this, yeah? It will be linear with 10 input features and then 128 output features. And then another linear with 128 input features and 128 output features and so on. Yeah, here's an example tensor. To run our model on this element, we can just say models brackets tensor, or we can do model.forward, but this is equivalent. You can choose whatever you like. Note that we did here like net 1, net 2, net 3, net 4, net 5. And we applied them sequentially. It's not efficient to create so many variables. And because this is a common operation to apply them sequentially, PyTorch has a several class and then those sequential. And we can put these elements in an end sequential here. So instead of doing forward with self.net1, self.net2, and so on, we can now just call self.net, and the result will be exactly the same. Yeah, so we put these layers sequentially in an end.sequential, and this means that they will be applied sequentially. Also, there are some other predefined classes like an end.module list or an end.module dict, which are similar to Python list or Python dict. And maybe in some cases you want to use them. It depends on the task. The most common one is an end.sequential. Yeah, and as you see here, your print looks exactly the same, but you have only one variable. We can calculate the result. You might ask me why here we got such output and here we got such output, which is different. Can you answer this question yourself? Yeah, weights are initialized randomly, and we didn't like fixed the random seed or like how random works anywhere. And even though architecture-wise they're equivalent, we get the different output. I will prove that they're equivalent a bit later. So it's not mandatory to write everything in one class. So it's not mandatory to have like only class my model sequential. You can create custom layers or custom subclasses. Just all of them should be subclasses of an end.module. Several classes, and each one contains its own, like for functions. If your functions does too many stuff, that's a bad function. You can split one function into several functions, and that will improve the readability and the quality of your code.
That each of the subclasses has its own semantic meaning. We will cover a case in transformer lecture.
Yeah, or if you, for example, I guess here I will also show something with residual connections. We will see. Let's say here you have this image, yeah? We can say this idea of having like convolution, ReLU convolution, and sum is one subclass in PyTorch, and use it like this all the time. Also, having subclasses allows us to avoid copy pasting. If you want to use this block like 10 times, instead of 10 times writing the same copy paste, what we will do, we will create one subclass, and instead of copy pasting the whole forward step, we will only copy paste the name of the class. And it will improve the readability and the quality of the code. So, for example, my custom layer looks like this. The definition is exactly the same as for the full model, but this one does only linear and ReLU. And my model with custom layer uses such stuff. My custom layer, and my final NN.linear. Notice, by the way, that here I didn't like add activation here at the end all the time because I don't want to. I wanted to have like a linear output here. Yeah, and I still can call self.net, but here in an endosequential, I saved some space. It's a bad example because actually I wrote more lines, but you understand the point. Yeah, and
So the sub-modules that you find that all using sequential as well.
I can say,
I mean, maybe that wasn't my question, but the question that I really want to know is, it's okay to put a sequential inside a sequential. Because
it would be weird. It would be weird, but you mean
that's the thing, right? So you're
no, I put it like if I did it like this, this would be weird.
right.
But
It would work, right?
it would
It's just a chain of function call.
yeah, it would work, but it will be weird. But maybe my custom layer is still a sequential inside. But maybe I want to do like my custom layer plus I don't know, like something else, and again my custom layer. And instead of, and imagine here, I didn't have just an n.relu and a linear relu. Maybe I had something like this. So here I have only 2 lines, but if I used it like this, oh,
Yeah, my question was, I think, well, maybe other people are getting value from this.
like
I understood. I think the thing I was not following, my question was quite simple about the semantics, that it doesn't harm it.
yeah, that doesn't make things worse.
The submodule needs to have all. The submodule here has a sequential in it. Does it need to have that?
You could do it. You mean no? Your subclass has its own forward.
Yeah, that's,
Your
and that's a cheaper way to run. But less code.
The alternative is that you remove sequential, you just define 2 layers, and then forward you call them one by one.
Oh, no, it's
So,
so you say
Like
by-
x equals self.layer 1 into data, y equals self.layer 2 objects.
yeah, so you're gonna have like self layer 1, self layer 2, and you will need to define here how this forward will look like. Yeah, it will be like this.
Okay, so now I understand why. And sequential is basically passed through. Like,
Yeah,
it's okay.
yeah. Yeah, so here it just I use an n-sequential for an example purposes, and because imagine you have some long and end sequential, which is the same here and the same maybe somewhere else in your network, and instead of copy pasting this large sequential, you just use one layer, my custom layer. Okay, good. Yeah, and here, if you look carefully, we'll notice that our model architecture is exactly the same inside. It looks a bit different from print, but like if you look carefully, it's the same model. And we again get the different output. And that's because the weights are initialized randomly. Yeah, if I run the same my model here, I will get different output because weights are initialized randomly and I didn't fix the seed. I can try to do it like torch manual seed 0. And here too. Now the output is identical because I fixed how my random works. Only one, my manual seed won't be enough because the seed is fixed here. I applied some random stuff and my model here won't start from the same seed. It will start from the seed which was changed by calling some randomness here. Okay. Yeah, so you can define an initialization scheme yourself. We won't cover how to do it. Sometimes it is useful to initialize some weights using like some predefined knowledge which you took from the paper. There are some techniques on how to do good initialization, and PyTorch itself does pretty good job, at least now, like after so many years. So usually you don't care about initializing weights yourself, but just to say that to prove you that all three classes that I created are equivalent, I initialize them identically with all weights setting to I set all weights to a constant value. To do this, I do this some complicated forward pass or forward for loop. And if my model is nn.linear, I say that weight data is tensor containing only ones, and bias also tensor containing only whites. Don't try to understand this code right now. Like you can look at it at home. It doesn't really matter. It's just some function that set all weights with the ones. Also, never do this in practice. Never set all weights to constant value because it is bad. Why? Let's do this. And notice that my output contains the same value in the first element and the second element. So because my weights are constant and they're identical all ones, the output is not different for different nodes in your fully connected network. And that's bad, like, because now you don't have any point to actually have more than one output. And if you do classification task, maybe you have n classes, you want to have your output of size n. And it will be bad if your vector of size n contains identical elements. So never set your weights to constant value unless you know what you want to do and why you need this. Yeah, and I set all weights with ones, and now we can see that all three models, as I said, they're equivalent. Okay? Never do this. Yeah. Moving on, we discussed how to create models in PyTorch. Are there any questions with this?
I'm thinking about the range for weights. Like usually, I was thinking somehow that it should be between, let's say, from 0 to 1, but now probably not. Like, what's the range for weights if you run them outside?
So there are different initializing schemes. One is called K-min, which uses some normal distribution, which is shifted by or scaled depending on which activation I use afterwards. So there is some theory, as far as I remember, that, for example, for ReLU activation, which is used afterwards, you need like one initialization scheme. And if you use something else, you need another activation scheme. Don't care about it yourself. PyTorch will do work for you. Karmin, normal initialization, uniform, orthogonal, sparse initialization, Xavier normalization, initialization, not normalization. Xavier from normal distribution, from uniform distribution. Also, there is initialization called Glorot. It's used in graph neural networks, and it does exactly the same thing as Xavier, as far as I remember. So just like there was a paper with two authors, and I guess one used one author and another used another author, but it's actually the same thing. Yeah. So optimization. We discussed how to create models. Now let's discuss how to actually train them. As you remember from previous code session, we had this function and we wanted to minimize it. We started from random point and we wanted to go to this minima. And what we did, we initialize some random current solution, initialize some optimizer with this current solution with some learning rate, says that we will do 200 iterations. And for each iteration, we calculated some loss, zeroed the gradients, because otherwise they will be accumulated at this beta as we discussed previous time. We did backward step. We updated current solution using optimizer.step. Also here, there should be like scheduler.step. I don't know why it's not here. So scheduler.step, it will be here. I guess because we didn't use scheduler, we use constantly right here. But yeah, in case you have a scheduler, it will be like this. And then we did some logging. I won't run it right now, but you will achieve this. So as we discussed previous time, to train your deep neural networks, you actually do the same stuff. You define your model, you define a data set, you define optimizer, you define scheduler. You should not forget about zero underscore grad. That's all. Also, we discussed like when to choose which optimizer and scheduler. If you want to reproduce the paper, you can use the schedulers and optimizers from this paper, but you should be careful. And if you don't know what to choose Adam W and Kassain Anilin as Atli suggested previous time. You can read this afterwards. Doesn't matter right now. So we discuss the data sets. To create a data set, all you need to do is create a subclass of the torch dataset class. You need to also define init. You need to define get item and length. But what I didn't say that what if you want to do augmentations or just some pre-processing, some transformation inside our dataset? So maybe we want to divide our image by 255, yeah, for example. Maybe. Yeah, to do this, usually we add here transform variable, or we define some methods inside our class. Here I used both. So transform is just some function that transforms our image or our input, our audio, maybe does some augmentation, maybe does some preprocessing. And we can also define method inside the class if you want to. And we will call it when we use get item. So X is, we have data, like all our data sets, the whole data set, it's maybe some matrix one. Here in this example, our data set is a random matrix with 1000 elements, and each element is a vector of size 10. Yeah, so we get element number index. We apply some pre-processing. Here, pre-processing is just, as example, for some reason, we subtract 300. And we can use transform. We can use both pre-processing transform as we want. X is equal to self.transform of X. And that's our output. What can be used as transform? So if we do not pass any transform here, because we said that initial transform is equal to none, so it does nothing. And here we check if it's none or it's not none. So initially all we have is this pre-process which subtracts 300. And we see that, yeah, it did something. Maybe we want to have our transform, which is also here like a strange example, it doubles the value. It does, all it does is multiplies input by 2. Yeah, so we can say that our transform is doubles the value, paste it here, and now we'll get the same thing, but multiplied by 2. Okay? And maybe you can use many transforms. For some reason, maybe you want to like have like doubles the value, then another doubles the value, and so on. And for this reason, you will use torch vision. It's like PyTorch, but from the same authors, it's a special part of PyTorch for computer vision. But it's commonly used for other domains because it has this useful torch vision transforms compose thing, which is equivalent to an n.sequential, but for transforms. So it sequentially applies all transforms which you pass to this thing. Yeah, we could say here that first one transforms image class to tensor, and second one is like double the value. I maybe want to do double the value for some reason, I don't know, 3 times, two times. Torch vision dot transforms dot compose will apply all these transforms sequentially.
Exactly, sequential model to this compose.
It will be strange because transforms, they're not like PyTorch model. No, they okay, you can do this because if you look at the source code for torch vision transforms, they're all instances of an n.model, subclasses of an n.model, and if you want to create your own torch vision transform something, you can also inherit from an n.model, but it will be strange code decision to apply some, I don't know, like an n-linear here, yeah?
So we start transforming the data once we have all the sequential layers.
No, transformer.
Like I think I got really lost.
So transform is when you take the item from your data set, maybe you want to pre-process it somehow or augment it somehow. It's the training and the model will be afterwards. So this happens inside your data set. As you asked previous time, we can do augmentations inside the model, but it is a separate step. So that's such pre-processing or augmentation of our data. Yeah, I don't know if I said this previous time, augmentations are used during training. Usually you don't want to use augmentations during test because augmentation will change your input data somehow and probably randomly, most of the cases randomly, and you don't want to have a random training set, randomly augmented training set. There might be the case when you want to do some transforms on validation set. For example, if your transform is normalization, you want all your inputs to have zero mean and uniform standard deviation, uniform variance. Then you can say that your transform here is normalization for training part. And for the validation part, it is still useful to have this normalization because if your model was trained on normalized inputs, its performance on non-normalized inputs will be it will be out of domain stuff. So it's better to make train partition as close as possible to test. And if you apply some normalization, some pre-processor stuff on training data, probably you should do this on test data, but it's not augmentations. Yeah, so here I suggest to work with a MNIST dataset. It's a common dataset for tutorials. You can download it directly from Torch Vision here. No, I don't want this. Yeah, and one example image from this dataset looks like this. So MNIST is a dataset with numbers, handwritten numbers, and your neural network should understand which number is written here. So this is 5. And your neural network should return class number 5. Okay. Yeah, we apply some, we do some data loader, we create some data loaders here. And for training data, you should set shuffle equal true. So it shuffles the data, and it's needed because you don't want your model to use the order of elements as a data set as a feature. Because it will maybe because your model, your data set is ordered like at first there are classes number 0s and classes number 1, classes number 2, it will hack the data set and it won't actually learn what makes image look like a 5, it will learn that if the order is like this, then it's 5, for example. Okay, so it's better to always shuffle training data set because you don't want your model to use order of elements as the feature. It will be cheating and it won't actually learn like in your test data or in real life, the order of elements won't matter. And therefore, this order feature is harmful for you. Okay. We have 5 minutes. Will be okay if I take 5 minutes more. Yeah, good. Yeah, so your train data loader with certain batch size has its own length, its number of batches in your data loader. It is different from train dataset length. It actually kind of equal to the length of the dataset divided by the batch size. But here it is not exactly equal. As you see, we have 469 in data loader and 468 here. This is because there is another parameter called drop last equal false. Sorry, another argument called drop last, and by default it is set to false. If you have a certain batch size and the number of elements in your data set doesn't divide by this batch size without the rest, so you will have many batches over batch size and one batch of the size which is equal to the rest. Yeah, so here we'll have one batch of size 96 because we can't create a batch size of 128 having only 96 elements left. We can do drop last equal true, and it will drop this last element, last batch of a different size, and we will have train data loader length equal to this length divided by 128. Okay. Yeah, so I will show you 3 model examples. First one is fully connected network. For image classification here, we do nn.flatten. As I said, to work with fully connected network, we need to flatten our image to make it look like a vector. In PyTorch, we can do it by nn.flatten directly in nn sequential, or we can do input data view like batch dimension in n-1, so it will also this view is equivalent to doing an n.flatten, and it will change your model from b height width to b heights multiplied by width. Okay. Yeah, but we will do an n.flatten here. We will show convolutional network. So instead of having an n.flatten, we will have convolution. There is convolution 2D, 1D, and 3D in PyTorch. We will use 2D because we have 2-dimensional input. We define how many input channels we have, how many output channels we want to have. Kernel size here is 3 by 3. If you have 3 by 3, we can also say this kernel size equal by 3, so this is equivalent. If you have, if you want to have the same kernel size for X dimension, for Y dimension, you can just set one value. But if you want to have different, like 3 and 2, you will need to use a tuple, a pair. Yeah, so kernel size, stride 1, maybe padding 1. This is also the default value, so we don't need to show them explicitly, but I just wrote it to show you that we can do this. Yeah, we apply again ReLU, maybe another convolution, and after some convolutions and ReLU, we can do the classification with some linear head, fully connected network head. We apply again an n.flatten. We should properly calculate the size of the this fully connected layer. That's a hard thing to do usually. So maybe you can like print or debug using ID, as Eric said, and you to define what is the proper size of this n.linear linear after flatten. Yeah, here padding is defaulted by 0, and I set it to 1 to make sure that my convolutions do not change the size of the image. So if my image was n by n, after having padding 1 with kernel size 3, my image will still be n by n. So I use it to calculate this n-linear more easily. Also notice that here I could do like an n, maybe max pool if I wanted to, with also kernel size 2. Then I guess it will be divided by 4. Let's show it like this for an example. Yeah, we can do more max pooling if you want. Let me check.
Since kernel size 3.3, it's return 3.
No, because here I used floating point division instead of integer division, and it was floating number. Yeah, and also show you not exactly ResNet, but ResBlock, and that's a useful case for subclasses. So usually you create a subclass for ResBlock here. How it looks like, as you remember, it looks like this. I have 2 convolutions, and I calculate these convolutions, and then I apply identity here. I don't do ReLU here because I did it inside these confs, as was shown here. Yeah, so it's possible to do ReLU here, or we can do ReLU here. So in my version of residual block, I do activation inside confs because I want to. Yeah, here I also have this downsample thing. So sometimes there might be a case that output plus X won't work because you have shape mismatch. Maybe because your input channels are 1 and your hidden channels, for example, are 32. Or your input channels are 3 and your hidden channels are 32. Then this will be a sum of something with 32 channels and something with 3 channels. And this won't work. To do so, in res blocks, you usually create a downsample convolution with kernel size 1. And all it does, it just here it transforms channels to a proper size. So here I will be sure that if my input channels are not equal to hidden channels, I can still do this summation here. Yeah, and my ResNet-like network looks like this. I will have 2 res blocks here. Again, flatten. And an n.linear again. Good. And notice that instead of writing this complicated forward and complicated init, I wrote it 1 time, but I can use it many, many times here. Okay. Yeah, so here I create fully connected network for an example, convolutional network, for example, and ResNet network for an example. I also need to define loss function. For classification, usually this is called cross-entropy loss. It is also predefined in torch.nn. I just call it and that's all. And we can look at it afterwards if we'll in the break maybe how it works, but if for those who want to. But yeah, let's for now say that we use this as a measure of how our predictions are close to the expected ones. And it uses probability of the class, predicted probability as input, and ground truth labels as targets. And what it does, it wants our model to make the probability for a ground truth target to be as high as possible, and for other classes to be as small as possible. Yeah, and here I define training pipeline, which is very similar to how we defined it for an example, simple example. I define function which calls train one epoch. So it's one way through one. It's one time when we go across the whole data set, across the whole data loader. That's what we call one epoch here.
So, oh, that's the entire one.
Yeah. All batches that we have in data loader, this is one epoch. Sometimes we can have infinity data loader, but we won't cover it today. So for now, data loader is finite. And the epoch is just one run through the whole data loader. So when you train your model, you need to call model.train at first, because some layers may work differently in during inference and during training. We didn't cover this yet. I'm not sure if we will cover this during introduction week, but some layers may act differently depending on whether you are doing training or inferencing. So you call model.train, you go across your data loader here. TQDM is just fancy stuff to show progress bar, how many batches you processed and how many batches left. One cool feature about PyTorch that you can train your models on GPU. This will make things much faster. And to do so, you need to call image your tensor to some device, where device is either CPU or CUDA, which means GPU. So you get this image and label from your data loader, you put them on GPU if you have one, you do forward step, model image equal output, you calculate loss, cross entropy between output and label, calculates loss, you do loss dot backward, optimizer step, optimizer zero grad, and scheduler step. This is exactly equivalent to what we did for a simple example before. Yes? And here I also calculate a metric for plotting average loss. As far as I remember, I did it also for the simple example. So just calculating average loss to do some logging. We have evaluation here. So evaluation is one run through the validation partition. It is used just to calculate metrics, not to calculate, no training, just to calculate metrics and validate how good the performances of our model is right now. We do exactly the same stuff, put something on device, calculate forward step. If we want to measure the loss on the validation partition, we can still calculate it, but we want to do loss dot backward, optimizer step or anything. We'll just calculate loss as a metric here. Okay. And also here, because we have classification, we calculate accuracy, because as we discussed previous time, I guess you asked the question, that accuracy is a better metric to define how good your performance is. So if your loss is close to zero, probably your accuracy might be still bad. You need to look at metrics that indeed correlate with the classification quality. Yeah, and the main function here is called train. And it says, okay, for epoch in range n epochs, we have, for example, 10 epochs here. For each epoch, we do train one epoch and one evaluation to calculate, to train our model for one epoch here and to calculate metrics on validation partitions here. And here we use train data loader, here we use validation data loader. And then there is some logging stuff to visualize the metrics. Yeah, here a device is CUDA or CPU. I have GPU in my laptop, so I can use CUDA. I can use GPU. We train for 10 epochs. I create my network, for example, fully connected network. I put it also on device, my model. If I want to use GPU, I also need to put my model on device, on GPU. I call optimizer. Here I use Adam. let's do Adam W as Atli suggested previous time. And as scheduler, I use cosine annealing. I need to define the total number of steps here, and the minimum linear rate. Here I state 1e minus 4. And then I will train my model. Here is fancy progress bar, which is helpful to decide how fast your model trains. Yeah, so we start from this. And as you see, the quality will, I forgot to put legend here. So blue line is a train, red is a validation, okay? Yeah, so as you see, loss is like this. Accuracy is on the right, pretty good. I will probably stop it because we don't have time, and I will just show the resulting curves. So for convolution network, we can do the same stuff, and the training curve will look like this. We can do the same thing for residual network, and you can see that residual network achieved much smaller loss, but the actual accuracy is also is almost the same. So that's why you should not choose your models based on the loss. Better to use some good metrics like accuracy, which indeed corresponds to your task, and to make decisions based on this metric. Okay. Yeah, and that's all for the code. Sorry that I took more time. Thank you.